Boa tarde. Esse microfone define, né? Que não tem erro. Muito boa tarde a todas e todos. Sejam muito bem-vindos, então, ao nosso curso aqui do PPG em Ciência da Comunicação da Unicinos, com a presença do professor Peter Krapp, da Universidade de Califórnia, Irvine. Esse curso, que é uma disciplina de um crédito aqui, oferecida pelo PPG em Ciências da Comunicação, ele também faz parte de um importante projeto que esse programa tem em combinação com o programa de pós-graduação em educação da Unicinos, dentro de um plano maior de internacionalização da universidade, chamado PRINT, e dentro desse projeto PRINT, onde vários PPGs da Unicinos estão envolvidos, os dois PPGs, então, de Comunicação e Educação, estão no projeto Transformação Digital e Humanidades. Então, ao longo do ano passado e também ao longo desse ano, e esperamos também para os próximos dois, nós teremos a presença de diversos professores, pesquisadores de instituições de ensino do exterior, de países com os quais esses programas entendem a importância de manter uma relação de desenvolvimento de conhecimento, de transferência de conhecimento, de aprendizado mútuo. E nessa perspectiva, o PPG em Comunicação propôs a vinda do professor Peter aqui para a Unicinos. Ele esteve conosco em 2018, também ministrando um curso dessa extensão, com outros temas. E a gente inicialmente agradece muito ao professor Peter por estar aqui hoje e ao longo dessas 2 semanas. Thank you, Peter, for being with us. Também aceitando o convite nesse período que ele está agora mais sabático em relação à vinculação dele com a sua instituição. Então, tinha essa janela de vir para cá em março, coincidiu também com a oportunidade que o projeto tinha de ter uma bolsa para trazer um professor nesse momento, e essas coincidências ajudaram bastante. E a proposta do curso também dialoga bastante, então, com essa temática mais macro da questão do tema Transformação Digital e Humanidades. Ele tem um nome específico, né? Digital Transformation and the Humanities, Contemporary Technoculture Dimensions for Research in the Social and Human Sciences. O Peter vai abordar temáticas do lugar de fala dele, que tem muita relação com algumas das questões que a gente trabalha aqui no PPG, especialmente aquelas relacionadas à dimensão do espectro das tecnologias, em especial na perspectiva da visada tecnocultural da pesquisa em comunicação. Meu nome é Gustavo Fischer, eu sou professor aqui do PPG, da linha de pesquisa Mídias e Processos Audiovisuais. Além dos encontros que nós vamos ter, então, hoje, nesse horário, das 18h30 às 21h30, amanhã, no mesmo horário, nossa terceira aula na sexta-feira, das 14 às 17h, na segunda, das 14 às 17h, finalizando na quarta que vem, das 14 às 17h. O professor Peter também fará uma participação na Semana da Imagem, que é um evento que nós teremos na próxima semana, durante 4 noites. O professor Peter Krapp fará a abertura do evento. E também estará conosco também para outras interações aqui junto ao programa ao longo dessas 2 semanas da missão dele aqui na instituição. Ele é doutor em literatura alemã e comparada pela Universidade da Califórnia, Santa Bárbara, e mestre em literatura inglesa pela Universidade de Stirling. Atua como professor de estudos de cinema e mídia da Universidade da Califórnia, Irvine. Seus interesses de pesquisa são cultura digital, história da mídia, comunicações secretas e memória cultural. Peter Krapp é autor do livro Noise Channels, Glitch and Error in Digital Culture e Déjà Vu, Aberrations of Cultural Memory. E coeditor de Medium Cool, uma edição especial do South Atlantic Quarterly. Certamente o Peter vai falar mais sobre as atividades que ele desenvolve, porque estão relacionadas com as temáticas que ele vai trabalhar. Aqueles que eventualmente não receberam o meu e-mail com o programa da disciplina, que é muito breve, ali eu coloco também a questão do prazo para entregar um resumo expandido, né, no qual vocês vão ter oportunidade de tentar estabelecer diálogos entre os objetos, temáticas, interesses de pesquisa de vocês com algum dos temas aqui a serem desenvolvidos. A gente também pode ir esclarecendo isso à medida que o curso avança, mas a ideia é que vocês aproveitem isso de alguma forma para o desenvolvimento das pesquisas de vocês. Nós vamos, quem já é aluno aqui da casa sabe, a gente normalmente faz aí um intervalo de uns 15, 20 minutos, mais ou menos aí 15 para as 8, mas também depende um pouco de como é que o Peter vai querer conduzir aí as atividades. Eu acho que em linhas gerais é isso. Nós também, esse primeiro encontro que a gente está fazendo o streaming e vai gravar, né, todas as aulas também. Quero também agradecer. That's good luck. Quero agradecer ao pessoal da Tradusul que está aqui, que vai fazer a tradução simultânea. A gente trabalhou com tradução consecutiva. I was going to pass you. Ok. Além disso, eu também conversei com o Peter para que ele, mais para frente, faça algumas recomendações de bibliografia atreladas aos tópicos que ele vai examinar, para que vocês também possam usufruir aí dessas oportunidades. Na Semana da Imagem, nós também vamos ter a tradução simultânea acontecendo, e também, na medida que vocês quiserem conversar com colegas que não estão matriculados, mas estão aqui no programa, que quiserem assistir isoladamente uma das aulas, obviamente aí não gerando crédito, também fiquem à vontade para fazer esse tipo de movimento. Para quem quer conhecer mais sobre o nosso grupo de pesquisa, tcav.com.br, ali a gente tem, né, mais informações sobre a Semana da Imagem. E o que mais eu posso falar? Para aqueles que estão chegando agora no programa, boas-vindas, né? Um bom ano para vocês, em termos de estudos e desenvolvimento. Aqueles que já estão conosco, segue o baile, né? Mas também o desejo de um excelente ano, para que a gente possa crescer como programa. E todo mundo agora vai colocar, ou aqueles que precisarem da tradução, os nossos fones, podem também nos alertar se tiver algum problema aí no áudio, para a gente ver se está tudo correndo bem. So, it's already an unforgettable visit to Unicinos. You don't have to clean that up, no problem.
I'm from California, water is precious.
Okay. Well, Peter, so thank you once again for taking your time to be here with us. It's been a long sabbatical for you, and please feel free to ask us anything if you need, and have a good class.
Thank you very much for the introduction. Thank you all for being here. Some of you I recognize from my last visit. This is my second visit to Unicinos, and I'm happy to be back now that the university has a partnership with UC Irvine, where I teach. And I want to thank Professor Gustavo. Closer to the mic, okay. That's the one thing I didn't get wet yet. I want to thank Professor Gustavo for making this return visit possible, and all of you for being here, and the communications program for arranging these lectures. I also want to thank Ms. Adriana for translating into your ears. If that ever does not work, or if you want me to explain something, or if you want to interrupt or ask a question, at all times just raise your hand, and I'll hopefully see that you want me to explain something, or go faster or slower or back. I'm used to it. You're used to it. So the more we can communicate to each other, the better. This series of lectures is going to be about internet culture. And already you should say, what? Internet culture? We don't need lectures about internet culture. That's our life. That's how we live today. We live enabled by the internet. But that's why today I want to take a really long view on communications and the history of media technology, where all three words are important: the history of media and technology. So my approach to it is explicitly to take the technology as central, technology as important. But I'm going to try to do that without having to talk about programming or math, right? So that's why I start with the history of secret communication. We have thousands of years of communicating that we arranged in trustworthy, verifiable channels. And now we take that for granted on the internet. We take for granted that the internet allows us to share all kinds of information on all kinds of levels of trust or verification or secrecy, confidentiality. So in the next few lectures, I will talk about information operations, propaganda, active measures, and then I'll talk about hacktivism, computer-based activism, and then I'll talk about new media, digital media, and human rights questions. And then as part of the Image Week conference, I want to talk about error on the internet, the error, miscommunication, and how the internet deals with the question of errors. And then finally, I want to look to future communities, future engagements that we have to figure out on the internet, including the spread of memes, the weaponization, the political use of memes, but also the proposal for the Internet of Things, the IoT kind of fantasy, which itself has a long history. So every time that I talk about internet culture, I try to talk about as long a historical arc as possible. So today is going to be thousands of years, and then the next few lectures will just be decades. So we're going to shrink, we're going to zoom in and shrink the focus. But when I talk about internet culture, I don't want to sound like I'm just talking about what happened today, what happened yesterday. So there's a long arc to the lectures that I hope, if you can attend more than today, I hope you will see that they somehow hang together. We don't have time today to learn the whole vocabulary that I put up there. I will go probably too fast through too many ideas, too many names of people, of concepts. But if you look to the middle passage here that lists the key developments, you'll see that more than 2,500 years ago, people already have techniques and devices for communicating in a secure or trustworthy or verifiable way. There's already a need 500 years before the Christian era, in ancient cultures, in the Hebrew culture, we know a device called atbash. Are there any scholars of Christianity, of early Christianity, of Hebrew scripture? No? You never know. You never know. You all might have hobbies that shed light on that. Atbash is a Hebrew phrase that basically just means you invert in Greek you would say the alpha and the beta. In Hebrew you say the aleph and the bet. So you just switch the sequence of letters, right? Or you say things backwards. So why would that be important? Why would a secret code like that be important in an ancient Hebraic situation? Any ideas? There are no hackers, there are no ancient Jewish. Any ideas? Well, there are two reasons that we can point out right away. One is that in Hebrew culture, there was a taboo against saying the name of God. God's name would not be said. There would be circumlocution. You would be indirect. And also certain bad names were not said, they were sort of alluded to. So if you say it backwards, then you're saying it, but you're also not saying it. Right? You're being indirect. That's one stylistic method that we can see in Hebrew, atbash. But there's also, of course, already the trade relations, right? So you have all around the Middle East, you have people dealing with each other, trading. And whenever you trade, you want to have an exclusive relation with your trading partner, because it's a competitive advantage to somebody else to know what price she can give me, or what I'm offering, or what the terms of our agreement for delivery are, etc. Right? So before you get to espionage or intrigue or computer crime, etc., there are already several reasons to have confidential communication. Trade is an obvious one. Right? But before we have the professionalization of different roles in society that we now know, how many people can name somebody who needs secure communications today, whose work relies on secure, secret channels? You all know lawyers, right? Lawyers need to be able to do that. A lawyer needs to be able to communicate with you in such a way that there's confidence, right? There are other advisors that have the same role, right? In ancient Hebrew cultures, to a certain extent, in ancient Christian cultures, to a certain extent, priests can have that role, right? You can confide in a priest something that you don't want everybody to know, right? Whether it's a confession or whether it's some other kind of role, right? Confidential advisors. Today, lawyers do that all day. Doctors, right? If I want to ask my doctor, I have these symptoms, I'm bringing the coronavirus to Unicinos. I don't want everybody to speculate about that. I want that to be a private, protected conversation, right? Who else? Lawyers, doctors, who else has a need for secure or secret communications? We already know business people, doctors, lawyers. Yeah. And of course, the military, right? Politicians and the military, or any kind of organized apparatus that is defending the interests of one population, one group against another, you don't necessarily want to be transparent for them. So it's not surprising that we see some ancient technologies like the skytale, the second word here, S-C-Y-T-A-L-E. It's a Greek word, ancient Greek word, also around the same age. It's a pretty simple device. You take a staff, a stick, and you wrap a piece of parchment or animal skin around it, right? Sort of in a spiral. Now if I write on it, I can read what I wrote. If I untie it, the letters are out of sequence, right? So I can write this on a staff. If I'm really smart, it's one that is conical, so it changes in width. The thickness changes, right? So the spread of the letters is uneven. This is an interesting concept to keep in mind for later, right? The less predictable the distribution of my letters in the encrypted messages, the more secure. Because now, if you intercept I'm going to throw this at him in the back and send him to another part of the campus with a message. Now, if the message is intercepted by somebody else, they don't have the right kind of conic staff to wrap it in such a way that it's safe. For military messengers, for business messengers, that kind of thing. You'll see a bunch of names on here. Caesar is pretty famous as, why is Caesar famous? Julius Caesar? the Roman emperor, not the inventor of the salad, the Caesar salad, but the important Roman emperor and military conqueror of large parts of Europe. Remember, these ancient Greek, Hebrew, and Latin Roman cultures, not everybody can write and read, right? So already being able to write a message and sending it is kind of secure from 90% of humanity. But if you're Caesar and you're dealing with a widespread campaign across multiple, what we now call countries in Europe, multiple parts of Europe, far apart, and you need to communicate in a confidential way with your commanders in the field, with your troops, you're going to try to think of a device that, even if the message is intercepted, it's not going to be clear. It's not going to be obvious what your intentions are. So Caesar comes up, there's going to be another slide. Caesar comes up with, there's Caesar, with what he considers a pretty secure way of encrypting his messages, which is by taking the fourth. I know not everybody wants to read Latin. I'm one of those people who had to learn Latin in school. So he switches letters 4 spots in the alphabet, right? So D for an A, etc. So the Caesar cipher takes the Latin text of his message and just shifts it, right? So it's a transposition or a substitution of letters, right? He shifted down the alphabet. And of course, it's not that hard to write that way, and it's not that hard to decipher as well. So it's pretty efficient, right? His commanders, the class of officers, they're literate. They can read, they can write, they can decipher that pretty easily. Let me go back a little bit. Now, there's a long period where I just say Arab cryptology. That's really brutally unfair to what happens in the Middle Ages. For several hundred years, the advances in coming up with ideas, practical but secure ideas for communicating in trade, in military, in diplomacy, they're advanced by the Arabs. Any ideas why that might be? Any history buffs who understand what happens with the Arabic populations? They're the ones who spread out at that time, right? The Romans have long lost their empire to all kinds of other populations, but in between 700 and 1200, the Muslim, early Muslim Arab populations flourish and spread all over Europe and the Middle East and into the Far East. They have very, very long trade routes, and they deal with people whose language is very different from theirs. Does somebody know any Arabic? I spent a year trying to learn Arabic. Okay, maybe don't translate this too literally because it's going to be a little impolite to, but I found that, before you can pronounce Arabic words, which have 3 different sounds, you really have to practice a lot. I didn't get very far in Arabic. It's difficult. It's hard. It's a hard language to learn. So they can't expect their trading partners from China or Spain, from Iran or who knows where else in Africa to learn Arabic, and they can't learn all of those different languages. So they're going to come up with something that's an ingenious idea, really an essential idea, which is to say, we're going to systematize. Now, this is before there's a discipline called linguistics. We're going to systematically look at differences between languages. And we're going to show that each language is distinct in the frequency distribution of its letters. Right? So French is different from English, even though they're closely related, different from Portuguese, even though they're closely related, very different from Arabic, very different from Vietnamese or Chinese. They have certain statistical properties, right? For one letter or for two letter or for three letter distributions, right? So in French, for instance, the most frequent three-letter group is ENT, which is an ending in French. Right? In English, it's THE, because the definite article is very frequently used. In German, it's DER, which is also a definite article. Right? So each language, the Arabs understand. If we use, and the Arabs are the ones who invent a lot of concepts that we now use for math. Right? So it's beginning to become a little mathematical. The idea of secure communication is securing against other people breaking my code, right? Not just inventing a safe substitution of D for A, but also preventing other people from understanding quickly what my message relies on. So they invent the concept of a zero. They invent all kinds of statistical concepts, and they understand that there are statistical differences between languages that they can exploit when they communicate securely across language boundaries. And then in the 19th century, you get the professionalization of cryptology. What do I mean by professionalization? I mean that there are people who are they find out, I'm not just good at puzzles, I can make a living being a military advisor, a diplomat, a tradesperson who invents codes. Now, there were some people before in the Renaissance. I'm going to show some pictures, but it's only in the 19th century that becomes basically a job, a profession, where it's still mostly about languages, knowing multiple languages, and understanding human psychology and understanding media technology of the time. And then, of course, I want to get into the 21st century because I want to talk about internet era things. But we're going to get there a little slowly. Right? At the bottom, you'll see also a summary of what I'm going to talk about. Before 1200, it's mostly about handwriting. It's wax tablets, the invention of paper. There's going to be some invisible ink. Does anybody know an example of invisible ink? Did you play with that when you were in primary school? Right. Certain kinds of things react with other things, acidic, base, apple juice, lemon juice, urine, can be used to write on paper, and it disappears because it doesn't have as much contrast as a dark pen. But then if I heat it up, for instance, gently without burning the paper, it turns brown. Right? Lemon juice will turn brown. Now I can read the writing. So there's all kinds of inventions of invisible ink. Then, of course, people try to make secure communication practical and convenient. So they invent some mechanical devices. So for a long time, this is going to be very simple. If you take a Caesar alphabet and you wanted to switch every D for an A, every B for an E, etc., you can have 2 rows, 2 circles with an alphabet, right? And you just rotate, right? And on the first day, you rotate by 1 letter. On Tuesday, you rotate by 2. And it would be more secure. If you don't use the same system every day, now it's mechanically made easy, right? So you don't have to always think about it or copy it. You can have a little device. And the devices become more and more complex until in the Second World War, right, only 80 years ago, people realized they've kind of come to the end of that development, and computers are introducing a new way, a new concept, a new idea. But for hundreds of years, the history of secret communication is the history of understanding that languages are different, that they have different statistical properties, that people have an interest in a confidential situation and a verifiable, trustworthy channel, and that certain kind of devices allow us to mechanize how that works. Right? So in some ways, it's the story of the humanities. In some ways, it's the story of studying human culture. Because if you go even to the most ancient stones with runes on them, I don't have the most famous one on here, and I don't have my keychain in because I'm not, carrying my office key, but I have a little miniature of the Rosetta Stone that I carry around with me. Does anybody know the Rosetta Stone? I see some people nod. Rosetta Stone, what is that? It's a stone tablet, a fragment of a stone tablet. It's about as high as I am now sitting down. It's not huge. And it has the same text in 3 languages. Right? Egyptian hieroglyphs, which nobody could read for thousands of years. Nobody could figure out hieroglyphs because it's a very strange system of writing. But it also has ancient Greek and Demotic. Demotic Greek, which is a different way to write the Greek languages. Now, scholars in the 19th century were very fascinated with runes and hieroglyphs and other secret to them forms of writing, and wanted to decode that, decipher that. Right? So Champollion, a French scholar, decided this piece of stone is the perfect exercise. If I just assume that these are 3 times the same text, and I can read one, I can teach myself to read hieroglyphs. Right? So to an extent, the study of history, the study of art history, the study of writing, the study of languages is the study of these deciphering experiments. Right? Now, of course, the Egyptians didn't invent the hieroglyphs to be secure against 19th century hobby scholars in France. Right? But sometimes I worry that a message that I might send to some of you, or you send me a message in confidence, securely, about business, about law, about whatever it might be, about health, there should also be such an idea as forward security, right? Not just confidential today, right? Pretend I actually work here full time, we have a dispute over your grade, and you challenge me to a jiu-jitsu match if I don't change your grade. Right? We don't want that kind of conversation to become known in the future. If there is a confidential channel, it should be confidential today and in the future, right? So I know that the hieroglyphs are not a secret system, but it makes you think about, how long does kind of secret be kept? How would I write a secret that is for this intended audience only and not for others? How long is that secret going to be protected? Until somebody comes, like Champollion, and says, I found a way to crack this, right? So think in both directions. Think about the person who has an interest in safe, secure, confidential, verifiable information, where if I get a message from my son who's sick at college, I want to know that it's from him and not from somebody pretending to be him, right? And I want to know that what I write to him back, whether it's about medicine or money or any other advice that a father could give to a son, is reaching him and not his roommates or some random person pretending to be him, right? So at any time when we communicate, we take this for granted, but in the 19th century, they did not take this for granted. Right? Yes, there was mailing letters, but they were systematically opened, right? You know this, right? It's like sending a postcard. The postcard is publicly legible by anybody who hands the postcard off to the next person. We pretend that a closed letter is not going to be opened, and some countries had laws against opening it, but let's face it, they were being opened all the time, right? So what I'm saying is that it seems paradoxical, it seems maybe even slightly perverse to study communication from the perspective of withholding communication, of hiding communication. But I think that all along, as long as humans have been communicating, they have been using words and methods and ideas and devices to make it secret, to make it possible to communicate a secret and to keep that secret. And that's certainly more and more true the more media technologies we get. You know, with radio, you know how radio works, right? If I speak into the microphone and the sound waves or the radio waves, they can carry on for miles and miles and miles, even into outer space. There's no boundary. They don't stop at the Argentinian border. Right? Radio waves just continue reverberating. So if I use radio and I want to communicate to my troops in the field or communicate with some other hobbyists who love, I don't know, what do hobbyists love? Model trains. And, you know, I want to only reach the people I want to reach and not the people for whom this is not intended. Radio is not perfect, right? Because radio can be intercepted or received by anyone. So if you're going to communicate on the telephone, on the radio, any other kind of technical channels that people have invented for media, in the newspaper, you're going to use a way to secure that message, right? Encrypt it, write it in such a way that it's only going to be legible and understood by the person it's intended for. Right? 19th century newspapers had not runic writing, but they had other ways of writing. You know, there was like these columns where you could write in a secret message that's only for your secret lover. And a lot of the names, a lot of the people that I listed here, sort of as a fun hobby, tried to break the encryption of other people's secret conversation. This is not necessarily always a spy military situation. Right? Some of the big breakthroughs in the 19th century in code breaking were made by hobbyists who were reading or trying to read lovers' conversations that were printed in a newspaper in an encrypted way, in an apparently secure way, where they proved if I use these statistical and other approaches, I'm going to be able to read what you write, even though you think it's a private conversation. Right? So runes, hieroglyphs, people come up with convenient devices that you don't have to carry on you. Right? So if you're caught somewhere crossing the border with a machine on you, you're already suspect. Right? You're already clearly a spy. So it's much easier if it's something that you can either remember or that looks very innocuous, like a little square like this. Now, if I take the alphabet and I put it into this square, what can I do? I can write my message as a series of numbers, right? So how would you write Unicinos with this scheme? 4, 5, 3, 3, 2, 4, etc. Do you see what I'm saying? Or if you use the bottom square, it's 2, 3, 2, 4, 2, 2, etc. Right? And as long as you know which square is being used, you can make sense of these numbers pretty easily. Let's say they come over the radio, they come over the telephone, but somebody else who listens to that, who doesn't know that this is the code, this is a square for the day, to them it's just numbers. They might not even know that 2 numbers are 1 letter. Is anybody already guessing why this is not very secure? Any idea why this could be vulnerable? Yeah. Yeah.
World War to send messages in the front. I read this before, and they were more protected than the Marines.
Yeah.
So
Yeah.
if they were intercepted, the enemy never know what was written, escrito, in the message.
Yeah. Exactly. So I'm going to get to that after the break. It's getting a little hot, and in a moment, in a few slides, we'll take a break, and then we'll get to the 20th century. But I already gave you the clue earlier. As he says, you can, at the moment you can see repetitions and patterns in a code, right? I might not know that it's 2 numbers for 1 letter. It could be 3, it could be more complicated. But as long as I'm only using 1 5x5 square, the probability in most Roman languages, whether you're speaking Portuguese or English, is that in the top square, there's going to be a lot of 1 5. Because E is one of the most frequent letters, right? And N in English, 3 3, there would be a lot. If my text that I'm encoding is an English one, there will be a lot of NN, 3 3 for an N. And T, etc., right? So there's going to be certain statistical properties for each language. If I even suspect that you're speaking Portuguese to the other person through this code, and I know what the distribution of letters in Portuguese is, I only have to look at this, or have a computer look at the numbers that I have listened to and say, sort this by what happens the most. Disregard what happens the least. So this is the Arab insight from the 8th century, that languages have statistical properties, and no matter how clever my scheme in changing these squares, I will always have linguistic patterns in there, in these simple encryptions. So this is a skittily that I talked about, the 2 illustrations of the strip of paper or parchment or animal skin that you can wrap around a stick. Here also, like I said, you could vary the distribution if you vary the thickness of the stick, but that's not very practical, so it's usually, like this microphone, it's a slight deviation, but it's not enough to really throw the distribution of letters in disarray. They're still going to be statistically orderly, in the same way that language is statistically orderly. The Caesar substitution doesn't change anything about the frequency of letters, right? If E is the most frequent letter in the message, in the language of that message, whatever I'm substituting for E is going to be the most frequent letter. Boom, I've just solved this encryption, right? Now I just have to shift everything else to wherever I found the E. Right? If this is not true for Portuguese, if some kind of other letter is one that's... Now, the weakness in that attack is short messages. If my message is really short, then it doesn't have the full statistical distribution of the language. Right? And if I don't know what language you're using, and I have to guess, then I have to try a lot of different languages. Right? So later on in the 20th century, we will look at people trying to decrypt messages in a language they do not understand. Right? There are Polish and English code breakers who do not understand German, but they break the messages. There are American code breakers who do not understand any Japanese, but they break the Japanese codes. Right? So we have to look at both the ingenious tricks to make messages secure and the attacks against making them secure. Now here you have Alberti. This is already the Renaissance. You have an inventor of making this Caesar shift more complicated. It's not just one letter for one letter or 2 numbers for one letter. Now here you can have words that will happen often in your correspondence, or even names of people, like on top, underneath the 8, you see the Duc d'Alba. You know, this is an important aristocrat. If his name is going to be used a lot in that conversation, it should be we should be able to substitute it either with a number 8, or with a letter G, or with a letter B, or with a capital E, depending on our need. Right? This already tells you that now you can encrypt differently. Right? So your E is not always going to be F. Your E is going to be different things. It can be a number one time, it can be a different letter one time, etc. Makes it more difficult to use that code, which is why people made these devices, right? So that you don't have to memorize multiple lists. Humans are good at these things, but not that good. You know, we're like puzzles, but you know, if this is about critical communication in a military situation, diplomatic situation, trade situation, you don't have forever. You need to understand as soon as you can, right? And you need to be able to respond as soon as you can. So the mechanization that begins is often around these kinds of round, flat devices. Some of them beautifully made out of metal and decorated. I don't have a lot of, I have lots and lots of pictures, but I didn't put them in the slides here. When I go to museums, they sometimes have these made out of bronze, out of silver, out of gold. You know that these are very precious objects. They're not carried around by soldiers in the trenches. These are, you know, used by aristocrats, by people working high up in the church, etc. They have the money. They can afford these devices, and they're as much a decorative or art object as a practical device. But there must have been practical devices made out of wood that didn't last, that we don't have in a museum because they have long broken or been lost or whatever. Here you have Blaise de Vigenère. Blaise de Vigenère is a 18th, 19th century inventor who says, if one alphabet for one other alphabet is not secure, how about 26 alphabets? So he takes the rotation principle one further and he says, my first alphabet, right, you can see A, B, C, D, etc. down, it's going to be on the left. And the first letter I'm going to do with the letter of my keyword. Right? If our keyword, the longer our keyword is, the more secure. Right? Even a keyword like unicinos, which has 2 N's, does it have 2 N's or 3 N's? It has 3 N's, right? Which has S's and N's in repetition, right? It's not a word that doesn't repeat. But I can go to the U column for the first letter and say, okay, if unicinos is my keyword, I go to the U column, and the first letter, what's your message? Give me a one-word message that you want to encrypt. Yeah? Okay. So if water is the message, you take the U column, you go down and find the W, right? Which in the U column is T. But then the second letter of my keyword is N, so you go to the N column, and you look for the A, and you encrypt it with where the A shows up. Right? You see how this works? Right? So instead of one Caesar shift, you have as many shifts as the keyword has, which makes it very difficult for somebody who is not the intended recipient. By the way, water was the message that she sent to you. But if you're not he gets it. He's opening his bottle. He received your message because he knew that unicinos was the keyword. If you don't know that that's the keyword, you have to puzzle through 26 alphabets. Right? Now that's an effort that humans do not enjoy. Right? That's something for machines. That's something for mechanization. Right? So the Vigenère square is still pretty simple. It's still a substitution, but now it's a polyalphabetic substitution. Caesar is a monoalphabetic substitution. Vigenère is a polyalphabetic substitution. Okay? It's the same simple principle, but by using a keyword, I can shift between the alphabets and make it more secure. There are some other historical examples of encrypting. On the bottom, the three images, that's actually from the War of Independence, United States against the British. They would use a mask. The picture in the middle is a cutout, and only if you have that can you read the words that will show up inside the mask, but the letter on the left is written to have a totally different meaning. Right? This is tricky. Right? You have to write the true message, and then you have to write something that looks plausible, that disguises your message. On the top right, this is a Mexican army cipher that was used in the 19th century. It's, again, very simple. It's just two. But now the alphabets are scrambled. It's not in a normal sequence, ABC. It's in a sequence that only the device will remember. You wouldn't remember that it's in a different order, right? So depending on what kind of scrambling you use, now here it is still in alphabet, but you can use different alphabets. You can even take it apart and put a different wheel on top for a different day, etc. Does anybody recognize the writing on the top left? It's actually explained below, but it's not obvious. So I want to know if there's a cryptological talent here in the room. A puzzler. Here, instead of switching one letter for another, or numbers for letters, you're switching the letters out for parts of the encryption that you see below, where you have two grids and two crosses, right? So A is this because it appears in the top left of the first grid. And B is this because it appears in that shape. You see it now? And T is this because it appears in the left corner of that X. And Y is this because it appears in the other side. Now, what you don't see, because it's in German, the annotation, one square is without a dot, and the second square has a dot. One X is without a dot, and the second X has an added dot, right? So that way you have space in two shapes to distribute all letters. And in this case, you even have space to distinguish between the I and the J, which many codes do not. Right? So you have more different signs. So you come up with the alphabet that is written at the top in this code. And of course, you and I could agree to distribute the letters differently. It doesn't have to be A, B, C, etc. It doesn't have to be with a dot and without a dot. It could be modified. Right? But as long as I understand you're using this distribution of the letters where A through R are in the squares, like the first 9 without dots and the second 9 with a dot, and then S, T, U, V are without a dot in the X, and the last 4 are in the X with a dot. Then I can understand this code pretty easily. Right? And at this point, we're going to take a 4-hour break so we can send messages to each other in that code. No. Just kidding. But, you know, amazingly long-lived code. I've been lucky to attend conferences on this for many years, and I got to know some people who are professional code. Water, W, okay, where is that? A, where is that? Etc. So Jefferson, even though this is the late 18th century, already correctly calculated that this makes it possible to generate a key space, meaning a possible expression of the text to be encoded, of 372 with 39 zeros. Right? Billions and billions of possibilities, which inversely means it's going to be that much harder to decrypt, to break that code. This device was lost to history until it was rediscovered in the Library of Congress, which is kind of the repository for everything in the United States, in 1922 by some scholar who by that time already knew of other cipher devices that worked just like this. Etienne Bazery, about 100 years later, also did not know about Jefferson, but also invented a cylinder cipher. This one is 20 wheels. Right? It's not quite as long as the wooden Jefferson model that you saw. This is in an era in France especially, but in Europe in general, where, as I said before, you know, people were making a hobby out of making and breaking codes after Champollion made this very fashionable by, you know, showing that you could read Egyptian hieroglyphs if you just puzzled enough. But it's also an era where that becomes a profession. So in this case, it's a French army major, and so he had a professional reason for providing a secure communication system for the French military. But it was broken pretty soon by one of his enemies, frenemies. Is frenemy a word I can say and have translated? Yeah. He had previously broken this other person's code, so they were going to try to attack his code again. And it stayed kind of a toy because of that friendly rivalry. And again, for a third time, a person called Parker Hitt, probably unaware both of Jefferson's device or the Bazery device, developed a device that he wanted to see used with just 12 pairs of wheels. So it's 24 wheels, 12 pairs. That he hoped the US Army would adopt. One of each pair had mixed alphabets, right? The pairs are already offset from each other, right? The offset is what you see already in Caesar cipher, right? A simple substitution, but here you have 12 pairs of them, so you multiply it. They're on a single shaft, and Hitt notice TH, which in English is a very frequent coupling of two letters in a row, and he thought, okay, if I want to encrypt TH, if I want to write TH in a secure way, in such a way that it's not obvious, I can see how this device could be used for that. So it became formalized for the military as the M94. The M94 was designed by Joseph Morborn, who took the prototype from Parker Hitt and said, if this is going to be hardy, if this is going to be something that we can use as soldiers, we need to make it of something that will survive being used in the field. So they made some prototypes of red fiber and rubber, but then they decided to make brass on a wooden base, the model. And then later, they started to use bakelite, which is a material that is pretty hard. It's not quite plastic era yet, but imagine something that's light and hard, where you can etch letters in. So the middle and bottom right are brass and bakelite. The top one is the metal prototype. It was approved by the Secretary of War in 1921. Right after the First World War experience, that we have kind of come to the end of the practical use of Morse code or other kinds of things over the radio. We need more secure communications for military purposes. It went into mass production after that political approval. They made almost 10,000 of these devices and also published a manual for it. I have some beautiful close-ups because, again, the NSA in its cryptologic history collection has some made of different materials. Nobody's quite sure which one was the most successful, which the most popular. Collectors love these. If you look on eBay, actually, I should say, please do not look on eBay. Do not go down that rabbit hole because they have become crazy expensive, really crazy expensive. People are collecting these machines. People are building, 3D printing their own versions of these machines. And sometimes a collector will try to build something to repair one of these to make it functional again because they break down. Bakelite doesn't last very long. The metal ones last pretty well. On the left, on the top, you see one that's made of aluminum. I almost bought one of those, but I'm just an academic. In 1933, there was a successor that was designed by William Friedman, who was one of the most important code designers of the 20th century. I'll talk some more about William Friedman after the break. If not, please remind me. Just send me a secret message that says William Friedman. He wanted to improve the security, and at first it was made with changeable paper around the wheels, and then on the right you see the 136. It's only in 1943 that both the M94, the mass-produced one of which they had made almost 10,000, and the M136 that you see here on the right were declared obsolete and insecure, and they were replaced by another model, very similar, the M209. What they have in common is that they have wheels with a mixed, unique alphabet each on an axis. You can have a ruler. You see on the right that's orientation. You put the plain text there, and then you select another row as a ciphertext. It's simple. It's portable. You can put. None of these pictures show how small they are. They're really they're about this size. They're a little longer than this. Right? So you can slip them in the pocket. It's not so secure that, if I catch you crossing the border from Brazil into Argentina and you have that in your pocket, I know you're a spy. But it's safe enough and practical enough for use by the military. And military are not always trying to disguise what they are. Right? So they just need to be in touch with each other. So there are multiplex devices with a 83-bit key, or 25 to this power of 25, which is actually, even though it's a very simple mechanical device, a greater possible key space than the Enigma, which I'm going to talk about later, which everybody hears about in the Second World War, the German device, or even DES, which is a digital algorithm that we rely on the internet, right, which doesn't have that great key space. Right? With that number of wheels, you can have a very, very large number of possible substitutions generated. So in short, and I'm going to take a break here, the original invention from the late 18th century was in use almost to the end of the Second World War, 150 years later. A number of wheels provide a cycle of repeating ciphers. If you select a row, it means that all the offsets are the same. If you were going to use a keyword, like in the visionaire idea, right? You switch the rows for each, right? The next letter is going to be encrypted with a different row, then it becomes even more complicated. Here's another weakness, right? It's not only that the weakness is that within one language, I have certain statistical distributions, right? Letters and letter combinations. It's also that, and that's the main reason they declared this obsolete in 1943, is that I can never encrypt an E as an E. Right? A letter can never represent itself. It's always going to be shifted away, which is why it's 25 to the power of 25, not 26. Right? The Vigenère square was 26 alphabets, but you're always shifting away from the original. With these mechanical versions of it, you're always shifting away from the original. And that makes it statistically possible for somebody who's patient enough to say, look, this is the most frequent thing. It never appears at itself. I found an attack. Right? So the Germans were able to use early IBM computers, pre-digital, mechanical devices to break the M94 in World War II. They understood that that's the statistical property of these. That's the downside of a mass-produced mechanical device. The enemy can get one, right? I capture him because he's not as good at jiu-jitsu as he thinks. I take the device, I can reverse engineer it, I can analyze it, and I can say, look, the one thing that this does not do is encrypt a letter into itself. Therefore, I can then infer other properties and I can try to attack this. So by April 1942, American messages were routinely understood by the Germans after about 6 hours or a maximum of 2-3 days. Now, that's still quite a lot of effort. In the heat of war, 6 hours, that's pretty fast. 2-3 days, not so great, but if you can follow the conversation on the other side, you know what they're planning, you know what they're saying, you know what their intentions are or were, and you can infer from that. All in all, over this 150-year history, about 27,000 of these cylinders were made. So it's the most produced device in the history of secret communication, which is why it's worth talking about. After the break, we get into the World War II device that's most famous, namely Enigma, and the consequences for the Cold War, where there's been some very interesting revelations just recently about what happened during the Cold War. And then we can see how that actually all matters for our use of the internet today, because there's certain principles that directly translate from this apparently esoteric field as apparently just my hobby, and you wonder why I'm talking about it. And we'll see that it actually teaches us certain things worth thinking about when we think about internet culture in general and secure communications over the internet in particular. So I don't know if you need just coffee or oxygen or nicotine or something else. Don't spill your water like I do. It's too precious, especially where I come from. Thank you for listening. After the break, definitely come with questions, so I'm not the only one who's talking. Thank you. Wheels, and the 3 wheels are going to be shifted against each other electrically, and then you have a keyboard, and then below that you have what even the English code breakers call the Steckerboard. It's like Stecker is a German word. You plug in wires, so you can multiply the way in which the wheels act in reaction to each other. Right? So it's still electromechanical, but they're trying to increase greatly the complexity that is possible with that kind of device. So you press down a key, right? W for your message water, and it goes through the 3 wheels, and it goes to a return wheel, Umkehrwalze, the German call it, and it goes back out. And it lights up a lamp for the letter that it encrypts as, right? Or in another kind of model, it would write that letter. It sends that letter as a message, right? So it's no longer simple mechanical, it's now electromechanical. It uses electric current that is sent through these wheels. So as you can see, the L in the middle, the Q down from the keyboard comes out as an L because the Q goes in, top right, it turns into a V, an S, a Y, etc. An X, a U. Each of these transformation is another shift, right? And it comes out as an L in this case. Right? Very, very complicated machine, but it was built in a very robust way, robust enough to be used on submarines, in offices, of course, but also on mobile command posts on the back of a truck, or even in a trench. So these historical pictures are of radio officers using Enigma set, enciphered with the plug of the arrangement of their unit and with the keyword of the day. Each day they're supposed to change the keyword, and in certain periods they change to plugging. And this is a point where you have to realize this is a step away from, a big step away from the mechanical devices where if you use it, you can still understand what the result will be. Here, it's basically black boxed to an extent where you press the key and you cannot predict what the result will be. If you make a mistake, you don't know that you've made a mistake. That's both the strength and the weakness of the Enigma. These are also very expensive collector's items, so my pictures are from various museums around the world. Of course, the NSA Museum has some, many science museums have some, many computer museums have some, Imperial War Museum in London has some. There are different models. When it was adopted by the military in Germany, there was, as it turns out, for the Germans, for the German side, an unfortunate level of competition between the different branches of the military. There's a sign-up list behind you. So on the left, you see the Army version. On the right, you see the Air Force version. And there's also a Marine version, the one that went into the submarines, which was, again, more slightly different. Each branch of the German military wanted to be slightly different. They were in competition with each other. And it turns out that's perhaps one reason why the Germans ended up losing World War II is because, one, they were too arrogant about the Enigma. They thought it was foolproof. They thought it was so advanced mechanically, electromechanically. It was so smart as a piece of engineering that it was unbreakable. And they became sloppy in its use. Right? If you think your device is unbreakable, you don't have to be perfect in the daily routine. And secondly, they didn't have one agency that would test whether this is still true. Right? So when I told you before the break that in 1942, William Friedman was in charge of the American effort of making and breaking codes, I really mean he was in charge. There was one office that was testing and verifying all the security efforts, whereas in Germany there was no such coordination. They were competing with each other, and therefore they didn't find out that these devices had weaknesses. Here's some close-ups where you see the wheels, you see the keys, you see the plug board below the keyboard, and on a daily basis, the people using these devices had to follow certain routines to make sure that the messages are being transmitted in a secure, trustworthy, verifiable way. And they made a number of consequential mistakes. One mistake was not really their own fault, but one reason, one redundancy that allowed Polish mathematicians to collaborate with English code breakers, the most famous of whom is Alan Turing, it was that many messages under that dictatorship of Adolf Hitler started with the same greeting, Heil Hitler. Or they would end with that. because it was a routine greeting phrase, right? So maybe, if I can make a disrespectful parallel, when you send text messages to your friend, you start with the same oi, or you end with the same, whatever, right? It's a redundancy, and if that repeats every time, the longer the phrase is, Heil Hitler has a lot of letters, I can say, oh, that phrase should occur quite a lot because these Germans seem to use that phrase all the time. Let's see whether I can find this, right? If I know that this kind of pronouncement by an officer begins or ends with that, let me test today's message and see if that's an H, if that's an E, if that's an I, if that's an L. And like the mechanical cipher machines that I showed before the break, with the Enigma also, a letter cannot encipher as itself. It's always going to be shifted to another letter. Right? That was a second weakness. And of course, another weakness in the field was that because people operating the Enigma thought it was so complex that it couldn't possibly ever be broken, they became sloppy with changing the keywords and the wires as well. Right? Because it's a pain, right? A new keyword every day. Wouldn't it be nice if I could just do what I did yesterday and only change it when my superior officer tells me, I need to change it now. But until then, I'm going to make life easy for me because this machine is unbreakable anyway. So there are a number of reasons why Alan Turing, the mathematician who you see in the bottom left, and other people collaborating with him at Bletchley Park, which is a really, really ugly country house in England, hideous. Has anybody been to anywhere near England, London, Cambridge, Oxford? Are kind of in a triangle, right? So London as the capital is about the same distance from Cambridge and Oxford, the two oldest universities that have a lot of academic talent in England. So they wanted to find a place for the code breakers, mathematicians and language scholars, linguists, and puzzlers that was away from London, because London is the capital, is a dangerous place for air raids, etc. But about the same distance from both universities. So they picked a place north of London, if you can see this, like about the same distance in the middle of the connections between Oxford and Cambridge and London. And it happens to be this country house, which today is a museum. They've preserved a lot of the house and its surrounding huts. They built these, they thought they were temporary buildings. On the top you see an aerial picture of these barracks that they've put up around. Many of them are still there. So you can go into the hut, you can go into temporary buildings, because the main house very soon was too small. Several thousand people ended up working there under the direction of Dilly Knox and Alan Turing and other code breakers, trying to understand how are these German devices wired. And they did not, in that case, these are big, they're bigger than a typewriter. They did not actually capture one to reverse engineer. All they had was the scrambled messages to go by. The scrambled messages would go out over wire, radio, sometimes on paper, and you could intercept those. You can hear them, you can intercept them on wires. You can maybe sometimes in a RAID capture some of the print, the paper versions, but they didn't have the machine. So what Alan Turing had to do was to basically calculate probabilities in such a way that he could reverse engineer not the machine itself, but the principle behind the electromechanical enciphering, so that he could decipher it. So they built something that's called the Colossus. And if the Enigma machine, it wouldn't quite fit into my bag, but it's not much, it's about the size of this block here. The Enigma machine was about that size of the podium which the projector sits on. the colossus that the English built at Bletchley Park to break those messages was big enough to fill this room. And that's partly because it's one of the first computers. It's one of the, Alan Turing is known for the breakthrough of digital culture, right? So one of the fathers, if you will, the famously gay, shy mathematician, father of computing, who constructed it first in his head and then in reality the first digital computers. And Colossus, here you see some often the operators were female. They were taught just enough mathematics to understand how the machine worked. But many of them, if interviewed afterwards, said they didn't understand how important their role was. They didn't really fully understand until the war was over how consequential the work was that was done at Bletchley Park. So they built this electromechanical giant, very, very noisy too. It's very interesting to me that now we assume that computers, this is a much more powerful computer than what you see up there, and it doesn't make any noise unless I want it to play me, the Beatles, but it doesn't make any unforeseen or generic noise. These computers, one of the impressive things about visiting Bletchley Park is that they have a working replica that they can start up for a tour group, and there's going to be somebody there who knows how to keep it running and fix it, and it makes a really loud racket. So there are people working in 3 shifts through the night, operating these machines that are basically doing what's called a brute force attack, right? They're trying every permutation. Is it this? Is it this? Is it this? Is it this? Now, if you do brute force attacks on any kind of code, you have to be willing to spend a lot of time. That's why it was important for them to also guess correctly, eventually, what weaknesses might be in the practice of the Enigma, right? Not just the theoretical weakness, which Turing cleverly found out that no letter can encrypt into itself, but also the practical weaknesses of redundancy, not just the redundancy in the German language, but the redundancy of using the same greeting phrases or a certain kind of allusions to weather, to names, to locations, etc. Right? So once you have cribs like that, you're no longer just guessing at everything. You have an informed guess. Right? It might start with an H. Let's try to find where that is today, with today's scheme. And they became very quickly so good that they're actually reading almost all the German military communications after about a year of constructing this very large machine. So they made some amazing breakthroughs that led to the computers as we know them today. And the National Cryptologic Museum I told you about, I don't know who that guy is, ignore him. But I can't show you pictures of the inside because it's kind of, like I told you, it's kind of a dingy, they're building a really nice building now that's going to be a museum, but currently the collection is housed in like I told you, in a room that's barely twice the size of this. So they do not have a replica of the Colossus, but they do have, of course, several enigmas. So here I am posing with one, and it's a beautiful place to visit. If you ever get the chance to visit suburban Maryland, which otherwise is quite boring, stop into the NSA. There's one part of the NSA that you can publicly visit, and soon they will have a museum that shows all of their collection pieces. And actually, let me interject another story. The NSA was formed in the Second World War as an agency, national security agency for the United States. It's the largest employer of mathematicians on the planet. We don't know exact numbers, but last time I heard they were still the largest employer of mathematicians on the planet. And that's because they're very, very invested in computing, computational security, cybersecurity, both passive and active. Right? So defending against, but also attacking against other people's computer systems. And they're the agency with the most cryptologic expertise, probably, on the planet too. There are some very, very good Israeli agencies. The British are still very, very good. So the GCHQ, the government headquarters, communications headquarters, now has 3 locations, but also has an interesting main building. They recently had a show of their collection where they had to use a proper museum in London to show it. So we're just beginning to realize in the 21st century that the history of the computer is in danger of disappearing. We're in danger of taking for granted that everybody has computers, multiple, and it's not just these little ones, but these, and then there is that one, and then there's one in the gas station. There's one with that thing with the 4 wheels that takes you from place to place. That's a computer. It's not a car anymore. It's a computer with wheels. So we're taking for granted the omnipresence of computation, and increasingly as black boxes. We no longer understand how they do what they do, how they communicate with each other. We want them to communicate with each other effectively and efficiently and in a trustworthy way, but we no longer necessarily reflect on the roots of where that all comes from, which is why today I wanted to geek out on the prehistory of computing and the long history of trustworthy, verifiable, secret, confidential communication, because we so much rely on it now with all our devices. I got a SIM card, a Brazilian SIM card for my phone. It has a number. It's a unique number, I hope, so I don't get your calls or your messages or your emails, right? Do I know how that works? It's not that difficult to understand, but you have to think about some of these principles. How can I be confident that I get the messages that are meant for me, and that you get the messages that I send as from me and verifiable? So we already saw that this has to do with a little bit of statistics, right? At least a statistical difference between different channels, between different languages, between different media. That it has to do with trying to create as many variations as possible in going from a simple plain text message, water, to as complicated as possible a ciphertext version of it. Why as complicated as possible? Because I don't want Gustavo to know what I'm talking about. Right? The message water is just between us. Right? The message about my health, about my legal case, about my religious conversation, about my political beliefs, are just for the people I want to communicate with and not others. It's not that I'm somehow doing bad things. It's not that I'm hiding anything. It's not that I'm a criminal, cyber criminal, whatever, when I rely on that confidentiality level, right? So at the moment, people realize that these manual, mechanical, electromechanical systems have reached a limit and can be broken with mathematical means. That's another change in the history of communication, right? As big a change as the change from oral communication to written communication, right? When we didn't have mass literacy, you had to have speeches, you had to have sermons in church, political oratory in the public square, etc., to communicate to people effectively. Once you have writing, everybody can learn to read and write. We can now change the way people conduct their affairs, their business, politics, religion. Everything changes, right? Based on the fact that we now have mass literacy. People can read and write each other. People can leave messages even for posterity. Not just communicate now, here, but communicate to my grandchildren, communicate from my grandparents to me. Right? So media extends our range, and if we want that extended range to also be trustworthy, verifiable, secure, we face a real challenge. Right? I don't want to leave post-it notes or postcards with the most secret things. So the moment that this sea change happens and people realize that mathematicians are going to do this differently from the way that people schooled in languages and some statistics and some mechanics, that is one of the explosions of the computer, one of the birth hours of computing. Right? It's not just because the Second World War posed certain other technical questions. Right? I mean, it's true, and I've told you this and other people this 2 years ago, it's true that the Second World War was also very much involved in calculating ballistic trajectories, which are complicated, calculating weather, like fluid dynamics are very complicated, any kind of scenario planning, like what if this happens and then what if that, and what if. Computers are very good at that, so there was a need for computing that is no longer manual or mechanical. There's a need for the computer as we know it now. The digital computer is very good at that. But this is just as much part of the story. Communicating securely, securing your messages against misuse or miscommunication, and breaking into other people's secure communication systems was just as much an impulse, an impetus for the invention of the computer. We just didn't learn about it until much later, right? Because a lot of this was secret. Everything that happened at Bletchley Park was kept secret for decades. A lot of people who worked at Bletchley Park died before they were legally allowed to talk about what they did. A lot of them women. It's a big absence in the history of communication, in the history of media, in the history of communication in general, is that these women, thousands of women, were not allowed to talk about their role in Bletchley Park. And so if they're not talking about it, there's going to be no historical record about it. Right? So it's only recently that it was declassified to a certain extent, that we also have public communication. We have movies about women who are working in these kinds of roles, not just in England, but also in the United States and many other countries. It used to be that that's what you call a computer. Right? It was a person. The computer was a person, often a female clerk. You know, they were doing manual numerical manipulations of communication. And then it became automated. It became the Turing machine. It became the black box computer. Right? So this is a very important point in the history of media in general, and in the history of secret communication in particular. With the invention of the Turing machine, now you can manipulate numbers and other signals much more efficiently, and now, of course, much more quickly, because the speed of computation has increased quite a lot. And that machine, that computer, doesn't mind running through the night, whereas people who having to do these things at Bletchley Park, it was very, very tiring for them, working in a very noisy environment for 24 hours, trying to understand messages that were in languages they don't speak, they don't read. So it's a real impulse for digital culture. And once the British effort became known to the Americans, there's always been some collaboration in the Second World War, although the North American participation was a little hesitant at first. You know, there were a lot of people in the US who did not want to enter into the First or the Second World War. But once the cleverness of the Brits became known, there was a lot of collaboration. So the NSA, to the extent that it's now the dominant place of expertise in this, owes quite a lot to Bletchley Park, owes quite a lot to that original collaboration with the team around Alan Turing. But they became more powerful, partly because of their budget. It's a much larger country, much more prosperous country in the Cold War. And it's not the only agency. There are 23 secret agencies in the United States. If I told you the names of all of them, no, I'm kidding. Everybody knows the names of all of them. But you'd be killed by me by boredom. The CIA, of course, is also important. And I have a quick story about two quick stories about the CIA. What you see here is actually a work of art, a sculpture, that was commissioned by the Central Intelligence Agency as a decoration for its headquarters. You cannot go and see this because you're not allowed to enter the grounds without being an employee or an invited guest. But I have a friend who's a pretty famous non-governmental employee. She keeps telling me she doesn't work for the government anyway. She's quite a good puzzler, and she took these pictures, and I'm allowed to use them. She was invited to give a talk there about something else. Her name is Ilonka Dunin, and if you've read the Da Vinci Code, terrible book. I hope you don't know what I'm talking about. But she's in there. Nola K, the character in the Da Vinci Code, is an anagram for Ilonka Dunin. So Ilonka, Nola K. You see what I mean? Like scrambling the letters. Anyway, she's quite well known among people who love puzzling about secret communication and things like that. And Cryptos is a sculpture that, as you can see, has wrought iron metal with letters punched out. In the middle on the left, you can see the letters Cryptos, but all of the rest of it is encrypted. It's in 4 different sections. 3 of the sections have been solved so far. The sculptor Jim Sanborn worked with an NSA employee and also told the then director of the CIA what the solution to this is. It's supposed to be stimulating the creativity of CIA employees, I suppose, like all public art. I don't know if you have sculptures here on the campus, but stimulating their thinking. And at least publicly, we believe nobody has solved the 4th section yet. It's possible, like always in a contest between agencies, like between CIA and NSA, that NSA employees know what the 4th section says, but they have not disclosed that. And of course, Jim Sanborn knows, but it's been more than 20 years, and he has not given away the solution yet. He's getting impatient, I know. Sometimes if I have the chance, I go to meetings of people who puzzle around this, and he will sometimes be invited, and he will reluctantly attend and do his very best not to give away anything about what this message is based on. It's a work of art. It's not urgent that you decipher it, but it kind of brings me to a larger point that whenever we read cultural artifacts, whether a film or a book or a game or a website or any kind of communicative act, we're deciphering, we're puzzling, we're detectives. We're not just eavesdropping like the evil spy saying, what is she saying to her? But we're trying to make sense, we're trying to explain, we're trying to understand, right? So in a broader sense, you are all code breakers, right? Depending on what code you set yourself to in your master's or PhD thesis, you're deciphering, right? You're trying to semiotically or methodologically decode what is at stake, what is being said, why is this interesting? Whether it's a work of art, a public sculpture, or whether it's a painting or a novel or a TV show or a game or social media or whatever. Right, so in a broader sense, we can all learn some of the lessons from the history of encryption that I'm showing here. Does anybody know the TV show Homeland? There's a couple of episodes of Homeland which is about a CIA employee, a female long-suffering CIA employee who goes through all kinds of trials and tribulations. But in 1 or 2 episodes, she meets a military officer who's become a domestic terrorist. I'm hoping I'm not spoiling the plot for you here. She meets somebody in front of the CIA headquarters, but because they did not get permission to film there, they're not showing the real Kryptos. So don't be confused. If you watch that, they're showing something. He can actually pull up with a taxi in front of headquarters, which you could never do. And then he sees a sculpture that doesn't look anything like this. But there are puzzles like this, made by professional code makers as a challenge to, and maybe even a recruiting tool for the agencies that are in the business of breaking each other's communication. The other CIA story that's in the news currently that I want to quickly make a detour for, stop me if I'm going too late, or almost done, is that there's another mechanical device story that transitions to electromechanical and then computational with the help of the CIA. From the 20s on, Boris Hagelin, a Swedish inventor, had been making machines and selling them first mostly to corporations, to businesses, and then also to nation states around the world. But with a company that he set up first in Sweden, and then for tax reasons he moved to Switzerland, called Crypto AG, acting Crypto AG, Swiss company Crypto AG. I don't have slides for this because it was a very recent development, but recently we learned that not only did, I knew the first part. I knew that he, early on in the Cold War, had agreed with the Americans, who were his biggest customer, not to sell the most advanced machines to certain other nations that are not friendly with the United States. This is what you do in business. If somebody buys 194,000 of your devices, that's your biggest customer, and you're not going to annoy your biggest customer, right? He made $7 or $8 million in 1950s kind of money, so significant amount from the United States government. And so he entered into a tacit gentleman's agreement. You know what they call a gentleman's agreement, if they're not gentlemen. Anyway, entered into an agreement with the United States to not sell the highest level of encryption to countries like Egypt or Brazil or other countries that aren't in the NATO or in the Five Eyes inner core of Great Britain, United States, Canada, New Zealand, Australia, right? So only those 5 nations would get the highest quality machines, and everybody else would get lower quality machines. That was pretty much known. Even, I think, the African countries that were buying those devices knew they were not getting maybe the very best. But they trusted that this Swiss company, it's a Swiss company, right? How can you not trust the Swiss? They make really good watches, they make these devices, they work really well. What they didn't know is that Hagelin in the 60s was getting a little old, he was getting a little tired, and as we saw, the purely mechanical, the electromechanical devices, they were not as good as computers. And in the 60s, computers were becoming more powerful and more affordable, and computers could crack what the Crypto AG machines were doing. But he didn't have the expertise to build digital devices. So the United States said, do you know what? You have a problem. We have a problem. Why don't we help each other out? We will give you the expertise to build digital encryption that you can sell all over the world. You, in return, will sell your company to us, but not tell anyone. So from 1970 on, the owner of this Swiss company was actually the CIA. And from 1970 to 1998, they sold devices for the highest level sensitive communication to governments and corporations around the world that the CIA could read because they knew what the machines were. Right? So there's a lot of history to rewrite in the light of this. We know, for instance, that this helped the English against the Argentinians in the Falklands. Right? We know this now. We did not know that at the time, that they got a leg up. Because if you can read everything that the Argentinian politicians and military are writing to each other, it's a big advantage. And we have to be careful, though, about these retrospective claims, about these revisionist claims, even. There are people who claim that Bletchley Park, the effort that Alan Turing and others led there, may have shortened the Second World War by several years. That's possible, but we cannot prove it. Right? You don't know. This is like a counterfactual history. Science fiction, you could make a nice telenovela about that. What if Alan Turing had not been quite as clever or quite as lucky? There are such TV shows, of course. But we can't, as serious historians, we can't know what the difference would have been if Bletchley Park hadn't been as successful. How much time would that have shaved? How many lives would that have not saved or saved? And similarly, this crypto AG revelation that the CIA was actually the true owner of the machines being sold by an apparently neutral Swiss agency, a Swiss company. How much did they benefit from that? We will never quite know. Right? Obviously, Russia, China never bought from them because they have their own capacity, they have their own technology. They were the main antagonists in the Cold War. And they were not fooled, at least not by this scheme. But now that we, in the internet age, are communicating at a very, very rapid pace, at very, very far apart, and we trust that we reach exactly the person or the people that we want to reach and not random others, we rely on this kind of technical legacy. But it's become a contentious thing for a number of reasons. Right? Legislation is currently being proposed in the United States and has already been passed in Australia and in England that makes end-to-end encryption no longer okay, no longer permissible, with all kinds of arguments saying, with the same kind of moral panic arguments that you get about all kinds of other technologies that empower people. So you're going to concoct the worst case scenario about child porn or, the worst thing that you can think of on the internet. And you say, we cannot let those people hide. And you take away the right of 6 billion other humans to have a confidential conversation, a trustworthy, a verifiable conversation with their doctor or their lawyer or their priest, right? So I find it interesting. I always ask my students when I teach whole classes on this, by the way. You're only getting one lecture today, and then we can breathe and talk about more cool things next time. But I teach 10-week classes on this to my students, and I always ask them, do you support unbreakable encryption? And there are always some people who are doubtful about it, but there's always a majority among people your age who say, yeah, it's a good thing that I can trust in certain cases, not all day long, but in certain cases I need to know that this information is not going to be used by somebody else against me, not now, not in the future. We should do this here if I knew all your names, but I didn't even get the sign-up sheet, although I pointed it out to you. I know there's a sign-up sheet, and we could go around and say, who here believes that the Brazilian government, the Bolsonaro government, should be able to access all your communications? And who here believes that technology companies serving your needs, such as, Facebook, Twitter, but also telephone companies like TIM and Vivo and Oi, should be able to give you secure channels that are unbreakable even to the police or the military? Take 10 seconds to think about it. And I'm going to take a light poll. If you believe the government should be able to access encrypted communications, raise your right hand. Really? You're all child molesters and cyber terrorists. If you believe that technology companies should be able to use encryption that is unbreakable even to law enforcement, raise your left hand. Oh my God, nobody has any hands. If you are still awake and you want to understand what the next slide says, raise both hands. Oh, they've all gone asleep. Okay. It's a hard question, I know, I'm putting you on the spot. It's a difficult political discussion, right? What I don't like about the way that the discussion is going in Australia, England, and the United States is that there's moral panic being invoked. There's like a hysteria about the worst case scenario, about criminals lurking in the dark net. And if the FBI or the police cannot eavesdrop on them, then all hell will break loose. It's an argument that I don't personally believe, right? So I'm taking off my academic hat, and I'm giving you my personal preference is certainly not to give the government a back door or a master key, because governments change, priorities for governments change. Government agencies with that power are not always transparent about how they're doing what they're doing. We have plenty of examples of agencies like the FBI in the past abusing their power, abusing their charter, and not being held accountable by politicians. Sometimes we don't have the right politicians. We only get the best politicians money can buy. But somebody needs to have oversight. And I think it would be better, and this is my personal belief, you might disagree, but I think it would be better to have that oversight also include certain levels of competition between companies rather than creating monopoly. Information monopolies, even the most benevolent information monopoly, I trust less than a landscape where we're competing for the best offer. And that might sound like, something a liberal American would say, which is why I think maybe there's different opinions in this room. It's a different country and a different situation, and as many parallels as we might see between the Donald, the orange one, and Bolsonaro, they're different. There are differences between your country and mine, and the conversations are very different. But they're not as different as we'd like them to be, because increasingly the technology companies are global, right? Facebook, Twitter, Google, Microsoft. There's not that many. I could go on, but I don't have to go on because there's very few, and they dominate in a way that I also don't like. Right? So it's not easy. That's why I gave you an impossible choice. But I just wanted to see if you can still raise your arms. Maybe some calisthenics as part of the communication program, Gustavo. I've emphasized throughout that this also is about practical questions. Right? A theoretically perfect system is not going to do any good if you can't use it. To send your message, water, as short as it is, it's a very important message. If you need to send that in a confidential way, in an effective way, it can't be so difficult that you spend half an hour for that one 5-letter word. Many things are available, but not that practical for us to secure our online footprint. Why would I even want to secure my online footprint? I'll talk a lot about that in the next 4 or 5 lectures, but let me just point out that there's marketers tracking me all the time. It's not just a phone company that knows where I am. I'm voluntarily letting people surveil me all the time by carrying this device on me, right? I'm not even getting anything for it. Marketers track everything that I look up online. They know who I'm communicating with. They know everybody in my address book. They know everybody's phone number, email. If you know enough about whose phone numbers and emails you're communicating with, I don't even need to read what you text them or what you email them. I know who you talk to. I know who you are. Right? The former head of both the NSA and the CIA has publicly admitted that the United States kills people based on just metadata. Metadata is the information about who you are in touch with. I don't need to know what you're saying or what they're saying to you. If you're in touch with the wrong cluster of people, there might be a rocket headed your way. That's the official government stance, right? So we're exposed. We're exposed. On the internet, in the digital culture, we're constantly exposed, right? To some very real threats and some maybe trivial threats, right? Maybe marketing is not so bad in your view. Maybe advertising is not all evil, although I'm going to talk about evil advertising as well in information ops next time. But some of these aspects of the internet have become troubling, which is why sometimes we use passwords. For instance, for our email accounts, for our social media accounts, right? It's not so pleasant to be disrupted by somebody who's, even if they're just trolling or pranking or making jokes, you know, you wouldn't want to be misrepresented on your social media feed. So if you have the ability to use secure communications, that doesn't mean that you will use them if they're complicated to use, right? So like using passwords. Most people still use passwords that are way too easy, like 1, 2, 3, 4, 5. Gustavo, which is his official password, by the way. You can go and change your grade right now with that password. You know, we're lazy. We need something to be easy. It needs to be quick and convenient. If it's too complicated, sure, that's theoretically perfect, but practically it's bad. It's not just government spies that I'm worried about. It's corporations, it's advertisers, even in corners of digital culture where you least think about them. Is there anybody who does not play any games on their mobile device, ever? You never ever play a game on 2 people in this room. Right? You're in the minority. Most people have implicitly admitted that they do that, except for you 2 conscientious objectors. Whenever you do that, you're being tracked not just by the phone company and maybe the company that runs the game, but it's become convenient and easy for people who make the games to use an SDK, a software development kit, that is from a third party, right? That does all kinds of things for your game already. Right? So it's a pre-packaged solution. And in almost 100% of the games on the Google Play Store for Android and the Apple Store for Apple phones and mobile devices, almost 100% of the games have multiple third-party trackers included. So even the most innocuous game, I'm playing chess because I'm a dork. I'm old. Look at me. Like, I'm decaying in front of you. Right? I'm not even playing a cool game. I'm playing chess. Right? But multiple third-party companies that I have no official relationship with, I don't even know who they are, can now track what I'm doing. And not just the fact that I'm playing chess, but where am I? When do I play this? How often do I play this? What other apps I have on my phone? What is my phone number? Who is in my phone number list? Who is in my email list? What do I look at on my browser, etc.? A frightening amount of information that only these 2 people have not volunteered to give away for free. I'm not overstating this. I'm not making this up. Okay? So when you go online, as it says here in the cartoon, companies and governments can spy on you by monitoring your activity, which is why we sometimes use a VPN. Does anybody here use a VPN? A virtually private network? There are good reasons. I'm not going to ask. That's a private question. Why and which one? No, it really is. It's like asking the name of your doctor or lawyer. You know, I'm not going to go there. There are some good ones and there are some not so good ones. Some VPNs are also shady, and they will sell your information. They will pretend to do something for you, and then they will turn around and sell you out. But many VPNs are trustworthy. A very simple scenario. Let's say you're in Canoas or Novo Hamburgo and not here, but you want to use Unicino's services. Well, you have your Unicino's credentials, I hope. You can log in and use a library or access a website that is course only, restricted to students, etc. Right? That's where we use a VPN. So I can virtually pretend, I can be virtually present at the University of California, Irvine, to file a grade or to answer a query from my library or to talk to a colleague in the way that makes me a part of the institution. Right? It has nothing to do with child porn, cybercrime, international terrorism, or whatever. Right? A VPN is simply what I've been talking about all evening: confidential, verifiable, trustworthy communication between two nodes on the internet in such a way that they know this is a firm handshake. I know you're you, you know I'm me. We're not being, there's no man in the middle. We're not being eavesdropped on. Nobody's going to change what I say halfway through, etc. Which is why it says down there, a good VPN company can really keep all of some of the negative side effects of using the internet without that protection at bay. Here it says like a bouncer, you know, of course, it's a comic strip. It's a, you know, it's making light of the situation. A bad VPN company, as it warns you here, can perhaps even lead to more spying, right? There are some very serious situations where you need it more than you need it as maybe as a Unicino student. Say you're traveling in China. China does not allow the use of Google Maps. China does not allow the use of Facebook or Twitter, partly because they want to promote their homegrown corporate versions of this, Baidu, etc. And partly because they don't want Western propaganda, which we'll talk about very soon, to be spread among their many, many citizens in China. Right? So it's partly censorship and it's partly self-promotion. So if you, like me, visit China, you're going to need a VPN, because otherwise I can't use my Google Maps. I'll be lost. Right? I can't get into my email from behind the great firewall of China. So the VPN is basically a tunnel through the firewall. Now the firewall could also be a good thing. Right? Anybody here want to argue the Chinese side? I don't want to be biased. I don't want to be one-sided. You know, somebody should argue the Chinese side. They have reasons to protect themselves, like all nations increasingly have reasons to protect themselves against bad actors on the internet. All of the deliciously nasty things that I'm going to talk about in the next 4 lectures for this course are things that we want to defend society against. Fake news, hacktivism, possibly a bad thing, possibly a good thing, I don't know, we'll see. I'd like to cover both sides, right? There are a lot of things that a nation state might decide to protect its citizens against. Right? So VPNs are a little bit of a double-edged sword. Messaging apps, just one other example. This is a spreadsheet from a couple of years ago. It's not that up to date, but I found it really interesting that when I tried to arrange my return to Brazil, that I was trying to arrange a convenient channel to communicate with colleagues here. and WhatsApp is still so popular here, and I keep telling them, no, I'm not going to use WhatsApp, and I have my reasons. I use Signal. I'm not going to use Facebook Messengers. I have my reasons. I don't want to go through 10 weeks of stories. I have my reasons. I don't trust Facebook. I don't trust Facebook. And another reason is that I don't trust Facebook. I use Signal. So I convinced one person in Brazil to install Signal because it's a Swiss company. What could go wrong? No, joking apart, what you see here this is just one page out of a long spreadsheet on the Secure Messaging Apps website. Surely it looks different now than when I took that screenshot, but the question, for instance, is, does your company collect customer data and keep them? And you'll see a lot of yes up there. Is encryption turned on by default? Or is it something that I have to turn on, which is already a step that a lot of people are too lazy to do? Like if I have to protect myself every time, it's like having to put on a raincoat every time you go out. You don't feel like putting a raincoat on every day, just in case. Right? Few people are paranoid like that. Right? It would be much nicer if there were some kind of automatic raincoat that turns on that you don't have to worry about. Right? And what kind of cryptographic primitives, meaning what basis are they building their systems on? And you'll see some very complicated acronyms listed here. RSA and Curve and AES and SHA. These are all acronyms for different algorithms invented in the last 40 years or so. And I'm going to very quickly introduce you one last idea. I can't leave you without a proper headache. This is an academic event after all. So one more breakthrough in computing and in secure messaging was asymmetric communication, asymmetric encryption. Right? All of the systems that I've talked to before were symmetric. We both know what the key is. We both know what the key word is. We both know what the algorithm is, what the machine is, what the device is, right? And you have an Enigma machine or a cylinder. I have an Enigma machine or a cylinder. You have a satellite phone with that software. I have a satellite phone. They're reciprocal. They're mirror images of each other. That was the obvious way to do it until the 1960s when a team around a guy called Whitfield Diffie published a paper that really annoyed the NSA because it published an idea that an Englishman had several years earlier, but the NSA was able to suppress and not make public, meaning that there can be an asymmetry. It can be a very simple path to encryption that is very, very difficult to cross back, to reverse, right? It's as if the way from here over to Gustavo's seat were 4 steps for me, but the way back is 4 miles. And the answer to that puzzle Whitfield Diffie provided is something that we can understand without any math knowledge, which is it's factoring, it's multiplication. So who's my next victim? I have to wake up somebody who has no arms to lift, but can still talk. Very back. You can multiply 8 by 7, right? Which is 56. Now, if I give you the number 56 and factoring into, what numbers would give you that product? with a small number like that, we can still do it. If it's 8 by 8, we know it's 64. I give you the number 64. You know, okay, that's the result of 8 by 8. It's also the result of several other number pairs, right? There are certain numbers that are special. They're called primes. A prime number is divisible only into itself and certain special numbers, right? So they're more exclusive. They're special numbers. So one of the reasons that the NSA employs more mathematicians than the rest of the planet is just that. Testing the security of algorithms like that. If I can take a very, very long number and another very, very long number and multiply them, you can all do this. I can give you two numbers that have 20 digits each. You can multiply them. We've all learned how to multiply. It's slow maybe if you do it on paper, or you can punch it into a calculator and it's very easy and you don't have to even do it in your head. Your calculator does it for you. We can all do this, right? So his machine can have one number, my machine can have the other number. If they come together, they form the product. But if she's listening in to what we're saying and she only gets the product, the very, very large number that is a 20-figure number by a 20-figure number, she doesn't know how to get from that one large number to the two factors, right? So factoring is hard. Multiplying is easy. Factoring is hard, right? So a lot of these, where it says curve, they're elliptic encryptions that have to do with factoring or with multiplication of primes. What they basically do is they give you the little lock and the S in your web page, for instance, right? I call up the web page of, what's the newspaper that you read here in Brazil? O Globo. You call up that website, or you call up CNN or whatever. You call up the website of your bank, which, you know, nobody cares what paper you read, but your bank account should probably only be accessible by you. You want to make sure that it has the HTTPS, which means secured, right? This is a confidential, exclusive communication that nobody is going to intercept, alter, or steal your credentials or steal your money. Right? So that's the very simple answer to what happens between your computer and your browser and the server at the bank's end, or the doctor's end, or the lawyer's end, right? It's factoring. It's fast to do between two simple machines. It's very, very long to undo by even a very advanced machine that you could put in the middle, right? So eavesdropping becomes hard. That's why it's interesting to know these messaging apps, what mathematical basis do they use? If they offer you a secure connection, what mathematical basis do they use? You can also compare browsers on this, although the standards are not set by different levels. I'm going to talk about internet culture a little bit more later in the course. Right? So you should worry about that just a little bit. Now, somebody here, but you don't have any arms to raise anymore, but somebody here should raise your arm and say, hey, wait a minute. I have a simple student life. There's not that much money in my bank account. My doctor knows as much as my friends know about my health. My parents know everything about my sexuality, and so do my neighbors, and my grades are not that bad. Why should I hide? What do I have to hide? Why should I go through all of these hoops? Can't I just be an open, friendly person to everyone? And I say, I think you're lying to yourself. I say, and this is why I can't ask you, but I stipulate, I put to you, as I'm wrapping this up on my last slide, that we all have something that we would not want everybody to know, right? There's a reason why when you go to the bathroom, there'll be a door. because we usually don't do that in front of other people. Animals do that, humans tend not to. There's a reason when you go to a bedroom, there's a door. We don't usually do that in public unless there's been too many chimeras or whatever involved. There's a reason why, and I'm not being obviously I am the older bourgeois white male subject here, and some of you might feel differently. Some of you might feel that all of this, or cultural studies, all of this hiding of interiority and citizenship and so on, is wrong-headed, and it would have a better society if we didn't have so much privacy. But I don't feel that way. So like I said, sometimes I have to take off my professor hat and put on my private microphone. I think that all of us have some things that we do non-publicly, right? Even if you're that very happy person who has no money and no sexuality to hide, because it's all shared with everybody. So that's why there's offerings like data pollution solutions where you can evade marketers by crossing the wires for marketers who track you or who track your game use and say, if we can't prevent you from leaving traces online with everything you do, everything you buy, everything you read, everything you play, everything you say, etc., then let's at least make noise that covers up and that hides the fact that he doesn't even play games, which is also embarrassing. So let's all agree to cover for him and say, no, he's one of us, we all play, everybody in this class plays. Just a white lie. There's two people who don't, but we're going to protect them by covering them in the noise that everybody else. Do you follow what I'm saying? So there are all kinds of interesting. It's not just the HTTPS or the secret messaging that we might have about whatever, but there are many scenarios where we can think about our internet use in terms of a trustworthy, reciprocal, verifiable connection that has no hiding from the law or subverting law and order. It has everything to do with just being who you are. And you're not always super happy to be under the spotlight with a lot of people looking at everything you do, including spilling water because you know you will embarrass yourself. It's sort of a preemptive embarrassment, right? Acting out in public. So there are many situations where we have the right to opt out of constant surveillance, constant observation. We no longer live in a medieval village where there are no doors in the front of the bathrooms or bedrooms or courtrooms or whatever. We now live in a situation where we should have the option. I'm going to stop here and continue with it in a different direction next time. Thank you very much for coming. I don't know if I can make you ask. Maybe I'll have to buy a round of coffee next time or some other stimulants. I like guarana. I've learned some new brands. I'm gonna maybe find something more Brazilian for you to enjoy. And next time, come with questions. The class will be more successful if we have more interactions, even though it goes through Adriana's mediation. Thank you again. I know translation is very difficult. I've tried to do this in the past. One of the reasons my hair is gray, it's hard. So thank you very much. Thank you all for being here, and see you soon, I hope.